very common motif in organic chemistry is a diether system. Basically, something you're going to have to learn how to synthesize, in particular, are alpha-beta diethers. Now, when you see this pattern of oxygen, carbon, carbon, oxygen, oxygen, carbon, carbon, oxygen, you should immediately think of epoxide, because the structures of this motif generally come from epoxides. Also, if you look at the molecule here, it's also optically active. That's another clue that this comes from an epoxide. Now, the immediate product of an epoxide, when you react a nucleophile with an epoxide, is you get an alcohol. And alcohols can be converted into ethers, which that's what we have. Now, what makes these problems challenging is that you have two ethers. Either one of them, either oxygen, has the potential of coming from the epoxide. And so you have to take a look at each one and figure out which one is the better case. Here we have two ethers. We can make this bond as a last bond, or we can make this bond as the last bond. Either one has the potential of being the correct one. So, let's take a look at the red scenario first. In the case of a red scenario, the alkoxide that we would use is this alkoxide. We would react it with ethyl bromide to give us this ether. And to make this alkoxide, we'd simply treat the corresponding alcohol with sodium hydride. And this is what comes from the epoxide. Now, epoxides, in order to figure out what epoxide specifically this came through, you have to take the OH from the epoxide and your nucleophile and redraw the molecules so that they are anticoplanar to each other. So in this case, our nucleophile is a methoxy group. So if we draw this OH as a line, the ethyl group becomes a wedge. The methyl group becomes a dash, only directed downwards. The methoxy group goes here. And the propyl group becomes a wedge. Now this is the anti-configuration. It makes it a little bit easier to figure out what the epoxide was. The epoxide, in this case, you keep the stereochemistry of the carbon bearing the OH the same. And you keep the propyl group also as a wedge. Now, even though this carbon bears a wedge, and this carbon bears a wedge, an inversion has taken place. Have to keep that in mind, because whatever carbon is attacked ultimately gets inverted. Now the next thing you need to do is add your nucleophile. In this case, we want our nucleophile to attack the right-hand carbon, which is the less hindered carbon. So therefore, we want to use basic conditions, sodium methoxide and methanol. Let's start with an optically active epoxide. We treat it with sodium methoxide and methanol, gives us this ether alcohol, which is optically active. Deprotonation of the alcohol gives the alkoxide. The alkoxide plus ethyl bromide gives us this product right here. So that's one possibility. The other possibility is if instead of making this bond last, make this bond last. In which case you're adding methyl bromide to this alkoxide. This alkoxide is formed by treating the corresponding alcohol with sodium hydride. Again, we have our ether alcohol species that we need to redraw. So our nucleophile, in this case it's an ethoxy group, and our alcohol are anti to each other. Then we just draw our epoxide. We keep the stereochemistry on the carbon bearing the OH the exact same. And then whatever a wedge over here stays a wedge over here. Dash over here. We still invert the stereocenter that's being attacked, and we get this. In this case, the carbon that we want to attack is the more substituted carbon. So to preferentially attack that carbon, we need to add a little bit of acid, along with our nucleophile. In this case, our nucleophile is ethanol. We want this epoxide to be optically active. like so. And so, either way, if we take this optically active epoxide and treat it with acid and ethanol, followed by deprotonation with sodium hydride to give us our alkoxide, which we do with the substitution, gives us this molecule. Or we can start off with this epoxide, the red epoxide, and go through a base nucleophilic attack with methoxide to give us this alcohol, which we deprotonate and do the SN2 reaction. We get the same diether. The relationship between the two epoxides are the following. Here's the green one. If I flip that one around, that's this one. It's optically active. And if I move the red one right next to it, in the green one I'm missing a carbon. You see that they are actually enantiomers of each other. The two roots are very comparable to each other. If you want to get technical, personally I prefer the green root to the red root, mainly because this step right here has an alkoxide that's very hindered trying to do an SN2 reaction, as opposed to the corresponding step right here, the final SN2 here. This one is better. Methyl bromide, less hindrance here, less hindrance here. This gives the better SN2. But really, the two are fairly comparable to each other. So which one you actually go for depends on either you're given a particular epoxide to start with, or if not, then you can do this same analysis, go backwards to find one or the other.